warm welcome to everyone for this first presentation of the EC webinars of the year. We are still part of the same series on risk and hazards associated with space, which has a space weather flavor. Just to let you know, today we'll be talking about auroras. Next week, Ilko Doornbos will be talking about debris and satellite drag, and the week after, there will be presentations on GNSS and planetary exploration, and also on the use of artificial intelligence for these applications. So please stay tuned if you're interested. All these presentations are put online, and you're welcome to join them anytime. And so I'm Thierry de Witt, and today it's my pleasure to welcome Jean Lilensten from France. He's a senior researcher. The CV he said was very short, so I will invent the CV. From what I know from him is that he's, I would say, his field of expertise is planetary space weather, but he has played a seminal role in this European space weather community with the COAST action. And today, until very recently, he was the main editor of a journal Space Weather and Space Climate. And all of these have played a huge role in federating a European community on these themes. And he also goes very often to Svalbard to make observations. And so some of the pictures will be taken from the places where he performs observations. So Jean is really an expert in auroras, and it's also a good friend. So it's a real pleasure for me to invite him. And with this, Jean, I let you go. The floor is yours. And just a reminder for those who joined just now is that if you have any questions, please keep them, write them down in the chat, and we'll have time for questions, ample time for questions at the end of the presentation. So let's start. Jean, it's up to you.
Thank you very much, Thierry, and thank you to all of you for joining. So I will talk of the polar lights, and since I want to talk of the polar lights, I assume that you are all space weather enthusiasts. I will not talk much about the sun, but as you know, as far as polar lights are concerned, the sun is at the origin of it. So I suppose you all know about nuclear core, radiative zone, convective zone, because what I am interested in actually is the solar wind. This is a movie from stereo, so you can imagine that the sun is at the right side. There are two scales, so the large scale on the right and the small scale on the left. And you can see the solar wind, and you see how actually inhomogeneous the solar wind is. And this is what is the most important for the aurora. I would like to make a short reminder of the physics of magnetic field. You all know from the Biot and Savart law, you could also consider the Maxwell equations, which are a bit more complicated, that a magnetic field is due to the movement of electric charges. So if you have electric charges that are moving and you are at a distance, then you can feel a magnetic field. It's important because the solar wind is made of protons and electrons. It means it means electric charges, and the solar wind is moving. So it means that it carries its own magnetic field, which is called the interplanetary magnetic field. You all know that the sun is an active star, so just for the pleasure of looking at some nice movies, here is how protuberance is forming at the surface of the sun. You have the surface of the sun here, the sun and the sky here, and this is a Japanese movie. And you all know, of course, that there is a full bunch of cycles. So here we have many protuberances and we have coronal holes. This is from SDO. And you all know that the knownest solar cycle was measured from the solar sunspot, and it lasts between 10 and about 13 years. And so it means that first parameter that is very important for aurora is the solar sunspot number. It is called Ri or SSN. And when the sun is very quiet, there is no spot, no solar sunspot. So its value is 0, and it can be up to 150 when the sun is very active. This is actually a strange number, a strange formulation, which is still debated and has been recently recalibrated by our Belgian colleagues. I will not detail the electromagnetic solar flux because it is not important for the aurora. Its visible part is relatively stable, but its energetic part, the UV, the EUV, the XUV, and also radio part vary, and it varies like the solar activity. So it means that we have a second parameter to characterize the solar activity, and this parameter, for historical reason, is the flux at 10.7 centimeter, called the decimetric index F10.7. When the sun is quiet, its value is about 70, and when the sun is active or very active, it can go up to 300. It's a poor proxy. If we would create a proxy now, we could have much better ones. But this one is the historical one since almost 1 century after the World War II. You all know also that the surface of the sun is the place for eruptions, and again the frequency of the eruption, like the prominences and flares, evolve cyclically with the same solar cycle, like the sunspot, like the radiative energetic flux. So it means that we have many ways to characterize the solar activity. For example, you also know that there are coronal mass ejections. So this is Lascaux from SO. So the sun is hidden behind the mask here, and the size of the sun is this white circle. And you can see, and you are aware of it and familiar with it, that when the sun is active, we can have many CMEs. The corona is also moving like and changing, and it is changing over the cycle. On the left here, taken from SO, we have the sun during quiet time, and on the right side the sun is active, and it looks like absolutely two different stars, and that's very different. So here we have many coronal holes all along the sun, and here we have only one coronal hole on the north and one coronal hole on the south. That's characteristic of a quiet sun. So the characteristics of the solar wind is that there are different regimes. The slow solar wind, it's constantly emitted. It is variable in time and in solar latitude, but it is constant. The loss on the sun is about 10 to the power of 14 kilograms per Earth day. And the energy contained in the solar wind is much less than in the radiative energy, 200 times less. The mean velocity, to remember, at 1 astronomical unit is 370 kilometers per second, and the mean density is 5 protons and 5 electrons per square centimeter. But there is another regime, the fast solar wind. And the fast solar wind comes from the eruptions, from coronal mass ejections, or from coronal holes. And the loss is about 100 less in average than for the slow solar wind. And the energy can be much bigger, but it is localized on the sun, while the slow solar wind is emitted all over the sun. And the velocity can be up to several thousand of kilometers per second. I will show an example, which is during my last campaign, the last campaign of my group in November last year. And so we had a sun, which this is from SO, and again, we have a sun which was active, but not very much active, with a solar sunspot number not very high, a corona which was quite regular, but quite active, and we had coronal holes scattered all over the sun and crossing the solar equator. 2 days later, the 9th of November, we had a velocity of the solar wind, which was around the average. So you can see here on the upper panel, so about 370 kilometers per second. And we had a density in the solar wind, which was actually exactly the average 5 particles, 5 protons and 5 electrons per square centimeter. So the two indices that I was mentioning, F10.7 was 126, and the solar sunspot was 98, which is a middle, not very active sun. So just for this first part, remember that the sun is an active star. It has several cycles, and the main one is 10 to 13 years. This magic number of 11 years is not exact, of course, it's even not an average. This activity is characterized by several mechanisms, not only the sunspots, but the numbers to remember, at least if you like to read aurora forecasts, is the solar sunspot, or RI or SSN, and the flux at 10.7 centimeters. And there are different regimes of solar wind. The slow solar wind, remember, 370 kilometers per second at 1 astronomical unit, 5 protons, 5 electrons per square centimeter. But there is also a fast solar wind, sporadic, local. It can be potentially dense if it comes from CMEs or eruptions, and it can be fast but less dense if it comes from coronal holes. So the most important, discovery from the end of the 20th century is that all the solar activity is driven by the variations of its magnetic field. The sun is a magnetic star. And this solar wind travels through interplanetary space, carrying its own magnetic field, as I said, which is called the interplanetary magnetic field, IMF. And it eventually will hit the Earth. And the Earth has both a magnetic field and an atmosphere. I would like to make a short reminder of the physics and these very, very simple and basic principles. So you know that if you have a charged particle with a charge Q in an electric field E and a magnetic field B, this particle will be submitted to a force which is QE plus QV vector B, but at the stationary state, then the velocity is simply equal to the electric field times vector times the magnetic field divided by B square. Now, below, if you have now a charged particle which is in a magnetic field, but with a gradient of the magnetic field, forget about the electric field. So the gradient of the magnetic field can act as a force, and then the equation of force is written like this. It's a sum of the a factor times V perp is the perpendicular velocity, perpendicular to the magnetic field. So it's a factor with the gradient of the magnetic field, and the same, of course, with the magnetic field itself. And if you have a stationary state, then the velocity becomes the vectorial product of this gradient times the magnetic field, and you have this factor in front of it. What is important is that if you have an electric field and a magnetic field, Q disappears. Then it means that the velocity of the particle is in the same direction, whatever the sign of their charge. It is not the case if you have a gradient and a magnetic field. The velocity will be different for protons and for electrons. And then I will finish with physics. There is also the magnetic mirroring. So you probably all know that there is a value which is called mu, which is constant. And this value depends on the ratio between the perpendicular velocity and the parallel value of the magnetic field. Since it is constant, if B increases, then V has to increase also. But you all know also that the total energy is also constant. It means that if the perpendicular velocity increases, then the parallel velocity will decrease and eventually reach zero. This is depending on the mass of the particle. It means that it is almost 2,000 times more efficient for protons than for electrons. And now we can go through the theories of the auroral oval. There are many different theories, not many, but several different theories. They can be very complicated, and I only have 40 minutes, so I will go through two simple theories that complement each other, and several actually clash, but those two complement each other and allow to understand how the auroral ovals are created. I wanted to have an interactive way to talk to you, but it was not possible. So what I did yesterday was to take a movie of myself in my office, and I will comment what I was drawing on the board. So we have the sun, and the sun is sending permanently in space electrons. And of course, it is sending electrons over all the surface, and you could see the movies before, and also protons. Same protons are sent all over the surface, and it will eventually reach the Earth. So I am plotting the Earth. I will plot it in two different ways. One with the magnetic pole, north magnetic pole here, as if you would see the Earth from the side. And these are the magnetic field lines. And I will plot the Earth also as if you would see it from above one of the poles, say the North Pole here. So, of course, you cannot see the South Pole, of course. The direction of the magnetic field is actually from the south to the north. And you all know the Laplace force, which says that when the particle arrive, they will be deviated depending on their charge. So it means that the electrons will be deviated on one side of the Earth, and of course at any latitude, not only around the equator. So they are deviated and they will go around the Earth, and the protons, they are deviated on the other side. They start rotating around the magnetic field line, and they are deviated, and this creates a cavity. This cavity is, of course, called the magnetosphere. Inside of the magnetosphere, you are plunged in the Earth's magnetic field, and outside the magnetosphere, you are in the IMF or in the solar wind. But remember that those particles, they are rotating at the surface of the magnetosphere, which is called the magnetopoles. The particles cannot know if they belong to one or the other, because this is where the pressure force equate each other, that of the solar wind and that of the Earth's magnetic field. So about 10% of those particles enter inside the magnetosphere. But because there is a separation of charge, there is an electric field. This electric field is directed towards you, actually. So those particles that arrive inside the magnetosphere, they are in a medium where there is an electric field directed towards you and the magnetic field to the north. It means that their velocity goes back to the Earth, whatever the sign of their charge, they have to go back to the Earth. E, because the velocity is proportional to E cross B. And when they approach the Earth, then the magnetic field becomes stronger and stronger. Then forget about the electric field, because then the gradient of the magnetic field becomes very important. And it means that the particle will be in a medium where you have a gradient of the magnetic field and a magnetic field. And the velocity will be proportional to 1 over q. It depends on the sign, times the gradient of the magnetic field cross the magnetic field itself. It means that the electrons will turn around the Earth one way, that's the protons actually in this direction, and the electrons will turn the other way. Of course, they rotate on themselves. Huh? And it creates a current ring. But eventually, those particles, electrons and protons, will be trapped by the magnetic field. There are collisions. Huh? And when they are trapped, the protons, they will try to reach the magnetic poles, but remember that there is a magnetic mirroring. The closer to the Earth they come, and the bigger the magnetic field. And so the smaller their parallel velocities, they cannot go inside of the atmosphere. Only the electrons can. And the electrons will enter the atmosphere of the Earth, and they enter the atmosphere of the Earth on this cycle here, this circle here. This circle here is called the auroral oval. Okay, that's the first theory. It is a very pleasant theory because it allows to understand why the auroral ovals and then the aurora are so dynamic. It is due to this electric field. Remember, the solar wind is very, very dynamic. It means that this electric field is not a line, it's moving permanently. And it means that the velocity of the particles which come back inside of the magnetosphere is also moving permanently. And then because this electric field is dynamic, the auroral oval is dynamic also. Look, this is a picture. In this picture, you can see on top there are stars, and then you have the day side of the Earth, and you can see this dynamical auroral oval. Inside of the auroral oval, there are very few, there are some, but very few aurora. It is called the cusp. And you can see here all the lights of the United States below. So you see how big it is. There is also a southern auroral oval. So this one is the boreal auroral oval, and the other one is southern auroral oval. And I wrote that it is disgusting because since they are the same, my laboratory does not want to pay a trip to me to go to Antarctica to make experiments. Why is it called an oval? It's because in the midst of the 19th century, the geographers counted the numbers of aurora. They published 2 maps. This one is the German one, and there was also a British one. And they said, look, all the aurora occur between those 2 very dark lines here at high latitude. Inside somewhere there is the magnetic pole, and it has a shape of an oval. So we call it an auroral oval, but there is no reason for it to be oval. It was just by error. In the cusps, the energies of the electrons is typically 500 EVs. It is called the polar ray. It is relatively constant, although it depends, of course, on the solar activity. I did not enter the details of different acceleration mechanisms, but in the auroral oval, the electrons are accelerated and they can reach several hundreds of keVs. It of course depends also a lot on solar activity. So I will now go through the second theory, which complements the first one. So we still have the sun with protons and electrons going to space, and they surround the Earth in the east-west plane. I insist, the physics is in the east-west plane. They come back when entering inside of the magnetosphere, but here something different happens. What is different? You have this magnetic field directed to the north, and the gradient of the magnetic field, which is directed along the velocity. And so it means that there is a force, which force is, yes, this velocity is proportional to Q, and 1 over Q, and to the gradient and the magnetic field itself. So it means that the protons will go one way, and the electrons will go the other way, and they will eventually go around the Earth again. What is different in this theory compared to the first one is that here they don't have time to rotate around the Earth and create a ring of current. In this case, they will be trapped by the magnetic field lines. So look, far away, almost at the magnetopause, here we have electrons, and those, oh, okay, no. Here the protons, they are trapped, and they are trapped by magnetic field lines, whose lines are closer to the equator. But of course, because of the magnetic mirroring, they just can do back and forth travels. It is called Whistler, by the way. While the electrons, they can go, and you see here, it's closer to the pole, the magnetic field where they are trapped. And at about 110 kilometers, they enter an ionospheric part, which is conductive, and the electrons will travel horizontally, and eventually they will go away along a new magnetic field line, which is closer to the equator. So we have currents. When the electrons come toward you, the current is negative, and when they go away of you, the current is positive. So, I plotted in red the positive current, because it's like if you had a current carried by protons, and in black, the negative current carried by the electrons. So you have part of the ionosphere which is impacted by negative current and impacted by the positive current. But you see, it is not at the same place compared to the pole. The positive current is equatorward and the negative is polarward. But it is the opposite on the other side. So you have a negative current equatorward and a positive current polarward. And it looks like the auroral oval. Actually, you can start to figure out that you are creating an auroral oval. Those currents are called the Birkeland currents. And those Birkeland currents have been observed already at the end of the 19th century by Birkeland. And this is an observation of those currents inside of the ionosphere in the auroral oval. And it was already published in 76. So that's this explanation. Those particles, whatever the theory, will enter the upper atmosphere. The upper atmosphere is made of two different components. The neutral one is called the thermosphere, and the ionized one is called the ionosphere. There is in the literature a lot of, how could I say, it's unclear. Sometimes people call it fully an ionosphere or fully a thermosphere. It's wrong. The thermosphere is the neutral component, and the ionosphere is the electric component. And you all know that the thermosphere is mainly made of N2, O2, and O. Above typically 150 kilometers, O is the only or major component. And those particles from the solar wind hit actually the thermosphere. And it creates a lot of ionization, excitation, dissociative ionization, elastic collision. And all of those phenomena compete with each other. So say, for example, this is for atomic oxygen. An electron enters the atmosphere, hits the atomic oxygen, and if it gives 4.17 eV to the atomic oxygen will be excited in singlet S state. And then it will go back to the ground state by emitting a UV light, or it will go to the singlet D state by emitting a green light. And then this state here can be also excited directly by an electron coming from the solar wind. And but then it will go back to the ground state by emitting a triplet in the red. And you see here for excitations, there are many different lights that are emitted. And of course, you can also create O+, and O+ is very often excited. And by going back to the ground state of O+, it emits again light. And this is the case also for molecular oxygen. And here you see it's many of those lines are very important. Herzberg and Schumann-Runge, or the third negative band and first negative band, all those lines exist. And for N2, it is still more complicated. You have a lot of dissociative ionization. So all those states, when they go back to the ground state, emit light. These are aurora. An aurora is the effect of millions and millions of electrons entering the ionosphere, the thermosphere, every second, hitting millions and millions of atoms and particles, O, N2, O2, exciting, ionizing those particles, and those particles, when they come back to the ground state, give back the energy that was received by collision under the shape of light. This is called aurora. The spectrum of the aurora is very complicated. We have very few spectra, actually. This is one of them, published in '68. And you see that the wavelength is here in angstrom. And you see that it's very complicated. But actually, when you look at aurora, it is not that complicated, because there are some lines that are much more intense than the others. This green one here that I was mentioning is due to electrons going down to about 100 kilometers. And most of the time, as I said, the mean velocity of the solar wind is 370 kilometers. With this velocity, the particle can enter down below 150 kilometers and down to 100 kilometers. So since this is the most often the particles excite the atomic oxygen in the singlet S state, which emit green light. So most of the time, the aurora are green. If the electrons have smaller energy, they will excite the singlet D. Smaller energy also means smaller velocity. So they will be stopped at higher altitude, above 200 kilometers. And here they will excite the singlet D line, which will emit in red. So it means that above 200 kilometers, the aurora are red. And if the particles enter the atmosphere with a higher energy, a higher velocity, then they will go down below 100 kilometers, where they will hit N2 and O2. But in the visible range, the most important line emitted by N2 plus actually are that from the first negative band. And the most important lights are the purple one at 391.4 nanometers and the blue one at 427.8 nanometers. So you see actually few lines, although the full spectrum is complicated. When those particles enter the upper atmosphere, the electrons will perturb the external magnetic field, of course, because they are charged which are moving. So they create their own magnetic field. And this perturbation is measured by magnetometers, and it has been measured for more than a century. And the first geographers decided to create a proxy, which is often looked by aurora hunters. It is called KP. It proxies the variability of the geophysical magnetic field. And when there is no change compared to the average, then the geomagnetic activity is quiet, it is zero, Kp equals 0. And when there is a lot of geomagnetic activity, Kp equals 9. It's good, but it's not great. Actually, I never look at it, I must confess. P means planetary, it stands for planetary. So if I go somewhere, I don't care about the planetary disturbance. I want to know the local disturbance. So it's not very good. Why? You see, actually, most of the aurora hunter, they look at F10.7 and the solar sunspot number and Kp. But actually, I don't mind myself. Look, I said that the Earth's magnetic field is directed towards the north. Imagine that the south-north component of the interplanetary magnetic field is directed to the north as well. Then it opposes the Earth's magnetic field, like actually two magnets that you would approach to each other north towards the north. There is a repulsion. And then in this case, the particle will just go around the Earth as I was describing before. But if, and that happens quite often, if this Z component of the interplanetary magnetic field reverses and goes toward the south, then at about 10 Earth radii, it will cancel the Earth's magnetic field locally. And the particles of the solar wind will pass directly through. It is called the Dunge open magnetosphere. And so even if there is little solar activity, you will have a lot of excitation around this ring of current. Look, I come back to this experiment in October last year. You remember the sun was not very active, and actually Kp was not very active. It was 3, which is good, but not so active. But my group was looking at the magnetometer. Let's just look at the blue curve. The blue curve is the vertical component of the magnetic field. And we could see that this component was decreasing. It means that the Z component of the interplanetary magnetic field was rotating towards the south. And it means that many particles would enter. So it means that here, one has to go outside because aurora, if there are no clouds, of course, aurora will come. So an important parameter that is very little watched at by aurora hunter is dB over dt. And dB over dt, you can find it on different sites. This is the European Space Agency website, and you can have the forecast of dB over dt. So whether by the first theory via the current ring or the second via the east and west flanks or both, aurora are created. And I insist that the physics is not north-south. It is all the physics is contained in the east-west plane. I will just show you what it is not. What is not an aurora. So this is a cartoon that you can find on the NASA website, but we have the same on the ESA website. So because it starts, okay, the sun is sending electrons and then protons and solar wind, but then they do not exactly understand what goes on. So it goes north-south, and something goes outside of the Earth, you don't know what it is, and it will come back because it needs to come back to create aurora, and it will create a circle around the magnetic pole. This is what you can find on the web. It's wrong. I hope that now you understood the physics of the aurora. This is absolutely not what you can find on those cartoons. This is an aurora that was the first movie of an aurora in real time and with the correct dynamics. It was taken by French astronomers from the Paris Observatory, Jean Mouette, so you can see these dynamics in real time, actually. So green, remember, green between 110, 100 and 150 kilometers due to atomic oxygen. This purple and these white lines, N2 plus, at about 80 to 100 kilometers. And this amazing dynamics due to the dynamics of the solar wind through the intermagnetospheric electric field. Here you have, oh, excuse me, I turned it off too early. So that's another one. And remember, if you are here, you are a curtain, it means that electrons enter, go down, and they will travel at about 110 kilometers, 100 kilometers horizontally and go back up. When they go back up, they don't have a lot of energy because all the energy was lost when they were going down. So they will not create an aurora, and so it's dark. It's dark here, although you have electrons going up. So this is from the space shuttle. And I like very much this movie because on this movie, one sees very clearly the auroral oval. Excuse me again. So you will see it here, it's rotating. So the red line here, 200, 250 kilometers due to atomic oxygen. So you can see the auroral oval here. This is a blue aurora. I have seen a few blue aurora. This one was taken by one of my PhD students, who is now a colleague, Cyril Simon, working in Austria. And this was actually in the cusp. I said that there are less aurora in the cusp, but there are some, and that's in Svalbard. This second theory I was discussing is pleasant also because it allows to understand these auroral curtains. Remember, when the electrons are going down directed towards the Earth, they lose their energy, creating light, and when they go up, their energy are not high enough to create, to excite. So there are black zones between the curtains. This movie has been given to me by Thomas Ulish in Finland, and I want to thank him. I thank all my contributors. That's a full night of aurora with an all-sky camera. So the time is on the bottom left. So now you know everything about the dynamics, about the colors, and you can just enjoy it. Aurora can last many, many hours. And because of the position of the electric field, sometimes it is less intense after 1 o'clock in the morning, but sometimes I could watch aurora up until 4 o'clock in the morning. It can last the full night. And in 2003, I was happy enough to have a very, very, very big solar event. I tried to read. It was so luminous. I could not read, but I took a book And I tried to read, and I could see actually that there were lines inside of the book, but I could not see the letters. So it means that the light is not very strong. It means that you can see the stars through the aurora, but if you have light pollution, then you will not see the aurora. So if you want to see aurora, you have to go outside the cities, outside any light pollution source, and it must be night. There must be no cloud, because aurora above the cloud coverage, if you can avoid the full moon as well. And this picture was taken by Guillaume Grenoble, another of my PhD student, and here it's a comet, actually, this spot at the middle. This picture got the APOD, the astronomical picture of the day by NASA. So red, 250 kilometers, 220, green, about 110 kilometers. That was in Lapland, or the Sami country, in March last year. And I come back to this campaign in October. You remember the sun was not very active. Kp was equal to 3. The velocity of the solar wind was just the average, its density also, but we had a reverse interplanetary magnetic field. You remember? The magnetic field was going south. Look what Gael Saturn took as a picture. The aurora became very, very dynamic, and it filled the full sky. It means that even if the sun is quiet, even if the solar, if the geomagnetic activity is small, you have a chance to see an aurora. Over 30 years of observation, it happened only 2 times that I could not see any aurora. But you have to go outside and wait and wait and wait, even if it is cold. And now you know why it is so amazingly dynamic. So I will finish now. I love aurora, of course, you understood it. Something that I find very emotional is that when I look at aurora, because I understand the physics, and now you understand it as well, I know that I am in physical contact with the sun and with the cosmos. Thank you very much.
Thank you, Jean. Thank you very much for this presentation. For the course at the beginning and for ending with these amazing, stunning images. I think we need to be aware of the beauty of these events. So now we have some time for questions. If you have questions, please, or comments, please write them down in the chat. There were a few comments already that some of the graphs were not labeled. Okay, let's start with a question by I think, let's start with Larry Lyons. You have a long comment. I'll let you turn on your mic if you agree to speak up.
Okay, can you hear me?
Yes.
Oh my gosh, the system works. Yeah, you know, I want to understand the basic physics of the aurora, why we have auroral arcs. And the reason we have auroral arcs is because of the requirement for current continuity between the magnetosphere and the ionosphere. If we didn't have that kind of situation, we couldn't have the discrete auroral arcs. When we have flow shears in the magnetosphere, they map from the magnetosphere to the ionosphere. You know, they can have 2 directions, so they give you converging currents in the ionosphere or diverging currents in the ionosphere. If it's converging, you get upward field line currents. And if you look at the amount of current you can get from the electrons along the magnetic field lines for upward field line current, you find you can't get enough current unless you have a magnetic field line electric field that accelerates electrons down. And that gives you the energy of like 1 to 10 kilovolts that causes the aurora. And I think that's really fundamental for the physics of the aurora. And another thing that was, you know, emphasized by the beautiful movies that we saw and that he showed in his talk, and that I've seen thousands and thousands more, is how the aurora, you've heard of space weather, you've heard of substorms and the different phenomena that cause the space weather disturbances. And there's a variety of them, space weathers, substorms, streamers, auroral megabands, all of which are very important. And we have no mechanism for understanding those in 2 dimensions as a function of time. And what is the dynamics that's happening and what's driving them and what's going on. But we measure the aurora such in those beautiful dynamic images and understand what they mean in terms of here's the auroral streamers, here's the substorms, and put all that together. We have the one and only technique for understanding space weather, what is driving it and what it means. Thank you.
Yes, actually, it was difficult. During these talks, I decided not to go inside of the acceleration mechanisms. I found it too complicated within 45 minutes, but they are very important. Whenever I give a class on magnetosphere now, I don't call it a magnetosphere anymore. I call it a system of currents. There are so many different currents. And so I had to emphasize only a few of them. And but you are totally right. Currents are very important in the magnetosphere. There are many, many of them. I also indeed did not discuss the closed magnetic field lines and open magnetic field lines. I only mentioned the cusp and the polar rain, but I know, but I only had 45 minutes and I wanted just to give the basics. But you are fully right, of course.
Yeah, if you look at the aurora and think about it in terms of connections to the solar wind, what you find is, and finding more recently, is that if you look at the the day side aurora and then the polar cap arcs and patches, you can see the connections from the day side all the way over to the night side, and how the whole coupling is between the whole system is leading to what we call space weather. So it's really amazing.
Okay, thanks. We have a comment by Elon. I guess it's Elon Roth. Maybe I'll let you speak up because it's not exactly what you wanted to ask. Elon, if you can turn on your mic. Yes, go ahead.
Can you hear me?
Yes.
Yes, very short. I just wanted to emphasize the point that the solar wind, although it influences the effects in the aurora, an important event component is the effect of the magnetotail reconnection and all the processes which inject very high fluxes of electrons into the night side of the aurora, and they are responsible for many, many interesting phenomena.
Absolutely. Yes, actually, there are several doors for particles to enter the magnetosphere, and you are fully right as well. Again, that was not a lecture on the magnetosphere, but of course. So I just mentioned the flanks. I also mentioned the subsolar point, but there are more. There are more. You are right.
Yeah. So now we have a bunch of very specific questions. So first of all, by Alan Ling, what causes an aurora to end? That's interesting.
Okay. It's the magnetic pole is not aligned to the geographic pole. So that's one of the reason. You are not always located at the same place compared to the auroral oval when the Earth rotates. And then you have this electric field also. You are not, compared to the electric field, you are not located at the same place when you are at the beginning of the night and when you are at the end of the night. And then compared to these plasma sheets that Ilan was referring to, you are not at the same place when the Earth rotates, and at the middle of the night, you are just in front of the plasma sheet and the electrons come. But when you are on the day side, of course, less electron will rotate and come. So that's all those configurations that make aurora. But you see on the pictures that I was showing, you have an auroral oval always. And with IceCat, the radar I am working with, we can see aurora not aurora, of course. We can see electron precipitation any time of the day, but the characteristics change.
Okay. So here's a very practical question. What is the best place to watch auroras in the southern hemisphere? Is it Chile, Antarctica?
I've not been to the southern hemisphere. I cannot answer this question, only for the northern hemisphere. I'm sorry. Maybe someone can in the audience.
Yeah, if someone has an answer or some experience with that, please feel free to write down in the chat. So one question by Miriam Sisson was, why don't we have emissions right in the center of the aurora? Why is the shape like that? Can it get smaller and change in diameter?
Sometimes aurora are very localized. Sometimes it is changing always. So it's difficult to answer this question. Sometimes you are very localized. Sometimes it is very diffuse. The mechanisms are a bit different, but the light emission is always due to the same excitation phenomena. And sometimes just curtain. So amateur astronomers use a classification of aurora, which I don't use at all, but you have many different shapes. So sometimes it's very localized. It can be just a spot of aurora.
So regarding the previous question, Harold Trace is suggesting that the best place to watch auroras in the south is exactly at the South Pole Station. And that's actually an intriguing question. So would it be the best to be at the pole itself or below the auroral oval?
Actually, not the magnetic pole. Not the magnetic pole. When I go to Svalbard, and I'm sure that in the audience, maybe many people have been to Svalbard, the aurora are not as bright as in the auroral oval, and there are much less aurora. It's very frustrating because in Svalbard, we are in the cusp, we are inside of the auroral oval. We can see the aurora on the south, on the other side of the mountains above Tromsø, and we can just see a very small amount of aurora. Of course, you can have some aurora in Svalbard, but don't go to the magnetic pole. Don't go close to the magnetic pole. Go under the auroral oval.
So he was mentioning the geographic pole, which is at -74 degrees.
Okay, that's good.
Yeah, okay. Misunderstanding, sorry.
Typically, the auroral oval is between 65 and 75 degrees in magnetic coordinates. So it's exactly this.
Okay. So another question by Andreas Pfoser, and he's asking whether there exist proton auroras.
Some.
Yeah.
Yes. Some. So it's because you see, I did not enter, but the details. But the magnetic mirroring, it depends also on the pitch angle, on the angle of the protons rotating around the magnetic field. If the protons rotate with a large angle like this around the magnetic field, then they cannot enter the Earth. But if the angle is very narrow, then they will enter far. They will go down in the ionosphere, in the thermosphere, and sometimes we have some proton aurora. So I could observe some proton aurora. Actually, with the eyes, it's impossible to decide if it is proton or electron. What we use is there is a blue shift in the hydrogen or proton lines. So we observe this blue shift because the protons are coming towards you. And that's how we can decide if it is proton aurora or electron aurora.
Okay. So we have another question by Franz Josef about the role of the energy of the electrons. Franz Josef, I'll let you maybe speak up. That will be easier so you can ask your question directly, since it is very specific.
Hello, Jean.
Hello.
Hello, nice seeing you, and hello, Tia. Thanks for organizing this very interesting webinar.
Hello.
I have a question. The electrons have an energy up to several hundreds of keV, as you mentioned, and I think measurements from rockets and they show that these electrons are really go very down deep into the atmosphere. On the other hand, the excitation requires only a few electron volt. So one would expect, I would expect that that auroral emissions can be seen much further down than 100. You mentioned 80 for the N2 plus, but I would expect that the emissions could occur further down. Or is quenching playing a role for the de-excitation of the excited state?
Yes, there is also quenching, you are right. Those electrons that enter with several keVs at the top of the ionosphere, say above 600 kilometers, and they start losing energy, and they create a lot of ionization. But when they arrive at 100 kilometers, they already lost a lot of energy. And there is this magic number of 38 EVs per to create an ion electron pair. So that's a nice way to see how many electrons can be created by a given precipitating electron. If this electron has 350 EVs, it will create only 10 secondary electrons by ionization. But yes, the reason is that they start losing their energy already at 600, 500, 400 kilometers. And the more down they go and the more energy they lose. And indeed, it's very difficult to go below 80 kilometers because when they arrive at this altitude, they already lost most of their energy. And also they enter a conductivity layer. And then the ionosphere becomes conductive horizontally for different reasons. It does not matter. So it is called the Hall and Pedersen conductivity. And it means that the electrons will be forced to move horizontally as well. It's difficult to them to go down.
Okay.
Thank you.
So Larry Lyons had a comment again about auroras occurring in the center of the oval. Maybe I let you speak up again so that you can be more explicit.
Oh, he talked about the center of the oval. Like we call that the polar cap, that the region of open field lines that directly connect to the, to the solar wind. And within the polar cap, there's interesting phenomena called polar cap arcs, which reflect shears in the flow of plasma over the open polar cap field lines that are actually mapping directly to the solar wind. How that all works and how that occurs, we really don't understand. But it's interesting. They give what we call polar cap arcs, which are generally weaker than what we see in the auroral oval, but they're nevertheless interesting. But I got involved a little bit with Qinghei Zhang and his group, and they recently talked about this very, very intense aurora that occurs like at 85 degrees magnetic latitude, where people don't look, and that really has a lot of attention. And we nicknamed it the space hurricane. So that's a region of very, very strong circular flows in the polar cap, and like very strong aurora with 1 to 10 keV electrons coming down, which happens under conditions of very strong BY, which gives strong circulation of plasma convection in the polar cap, and thus strong convergence of ionospheric currents. So it's all really interesting, and that's sort of an area of that connections of the space hurricane, and also the connections along the polar cap arc from the day side to the night side that deserve a lot more attention.
Yeah.
What I like the most actually on the polar cap is that the polar rain is permanent. And so with my instruments, I can measure the red line permanently. And to me, it's very important because I need long time measurements. And so I like those places very, very, very much. But you're right, there are still mechanisms that are not well understood. Absolutely.
You can measure the polar rain, and separate it out from patches that are propagating across. That's really cool. And can you look at the differences between like one side and the other side, and the differences in the polar rain from let's say the dawn side to the dusk side, which I think is another really interesting topic which nobody's ever studied. If you look at the electron data, it's real. So it'll be kind of fun.
Okay, I think we're getting close to the end. Again, I would like to thank you, John, for this very nice presentation. It's a long time we haven't heard about auroras. Many thanks to the audience for participating, asking questions. And so next week we shall have with us Ilko Doornbos, who will be talking about debris. And later on, the series will continue with GNSS, planetary space weather, and artificial intelligence for space weather as well. So you're always welcome to join, and you can also listen to the presentations on the website. And if you're interested in ECE activities, of course, you're also welcome to submit proposals for international teams to study such topics. This is what ECE is for. So again, many thanks to everyone. Have a good evening, good day, wherever you are, and maybe see you next week. And thank you.